All right, so yesterday we left off by drawing CO2. So I want to pick up by drawing the next one. If I can find my Promethean pens, anybody see it? No, it's not. It is actually a good call. My bad. Sorry, I was recording all that. I apologize. All right, so we've already done all the oxidation numbers. So let's do the drawing of SF6. Okay, so SF6. Now, the first rule is we want to list each element and how many of them are present. So what are our two elements? S and F. How many of each? All right, and we're going to multiply it times its valence number. What group is sulfur in? So it's got 6 valence. How many valence does fluorine have? 7. Okay. So 1 times 6 is 6. 6 times 7 is 42. So what's your total? 48. All right. So I've got 48 electrons I've got to deal with here. This is going to be a big one. Which element goes in the center? Sulfur. Very good. Now, never mind. We'll talk about it in just a second. So, pretty much. Yeah. I agree. I agree with you. Yep. All right, so we've got, let's see, 1, 2, 3, 4, 5, and 6. So that's kind of how I drew it. And then I'm going to connect up all my F's. Correct. All right, so far, how many electrons of my 48 have I used? Okay, 2, 4, 6, 8, 10, and 12. So what's 12 minus, or 48 minus 12? Very good, so I've got 36. Now, the thing that you're fixing to see me do is a very, very, very lazy way of doing this. On the real actual test, May 2nd or May 1st, please do not do this, okay? What I'm going to do, I'm just doing it for speed. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, and 36. Okay, so again, the line can also represent, but you make sure you put all those dots. On the real exam, make sure you put the dots, okay? So I just used all of them, and I'm out. Okay, so this is going to be my structure. There's no adjustment needed or anything like that. There's one thing odd, though, because you remember every element needs only 8 valence electrons. Now, there's one that needs less than 8, and who's the one that's boring? Boron is boring, right? He only needs 6. Okay, but when you look at sulfur, what's going on with sulfur? It's got 12. There's something weird. So some of you will look at that and say, that's not right. But what do we know about sulfur? Okay, very good. Write this for me. Okay, this is an expanded octet. Okay, remember that little story. It was Peter sips chlorine as selenium breaks crayons telepathically in X-Men. Those are all the elements that can hold up to more than 8. And sulfur is one that can hold up to 12. Okay? Peter sips chlorine. So phosphorus, sulfur, chlorine. As selena breaks crayons. So arsenic, selenium, bromine, and krypton. Telepathically in X-Men. So tellurium, iodine, and xenon. Okay? What's up? Yeah, come here. Okay. All right, so again, this is kind of one of those funky ones. Now, I just want to run through this. I'm going to erase all this so I can write it all down, but that was all pertinent. What is the shape of this thing? It is the biggest one. The reason it's octahedron, I know this is going to look really weird, and I really don't know how to draw this the best way. Okay, think about it from this perspective. Imagine actually this kind of coming out at you, and like this kind of being a face, this being a face, this being a face, this being a face, and there's 2 on the back side. It's 2 pyramids stacked on top of each other. Sure. It's a cube tilted, or the way I like to look, it's 2 pyramids stacked on top of each other. Yes, the bottoms are flat and they can stack. So you got points on each end. How many faces does a pyramid have? 4. Okay, well, if you've got two pyramids, you've got 8 faces. That's where octa comes from. Okay? All right, so that's kind of what's going on there. All right, octahedral. Is this thing polar or non-polar? Non-polar, so automatically what's your IMF? LDF. That's an automatic. Okay? All right, does anyone have... all right, if all of those F's started pulling out on that S, which F wins? None of them. That's why it's not polar. Okay? Does anyone have the bond angle for octahedral? It is 90. Very good. 90 degrees. And then the hybridization, which is the fun part. It pretty much, yeah. They can ask you any of these questions. Okay? So, S, P1, P2, P3, D1, D2. Okay? Sure. Absolutely. I absolutely will. Yeah, once I get to that, I'll print y'all. Yeah. Okay. All right. Yeah. Again, I know that this is not technically particularly pertaining to the information we're trying to talk about, but I think it's good for you guys to see it sporadically throughout. Yes, you don't forget it. Okay. All right, so the next one was NO3, right? Okay, so NO3. So same steps. Write down what you got. Write down how many you got. So 1 and 3. What's your valence number for nitrogen? 5. Oxygen is 6. So I've got 5 plus 18 is equal to what? That's right. So you can't do this one. Actually, let's do this. Okay. Let's make this nitrate. Yeah, my bad. I didn't realize that. Sorry. So here's the important thing. So there's two things. If you have your rules still in front of you, and I don't have them out with me, but at the very bottom, I think. No, there they are. Okay. No, look down there at the very bottom where it says notes. Okay. If it's a polyatomic, make sure to draw the molecule in what? In brackets. Okay, very good. So we've got to draw brackets, and I got to put my charge out here. So anytime it's charged, that's what you got to do. Okay. Now, you were right, Mason. Go back up there to 3A. 3A says, remember, if it's charged, plus or minus, add for a negative and subtract for a positive. Now, that's weird, but it should make sense. What does a negative sign technically mean? You gain an electron, and what are we counting? We're counting electrons. So do we add one or take one away? We add one, so we're going to turn that into 24. Okay? A rule sheet, yeah. Matter of fact, here, come grab both of these. Because we did oxidation numbers yesterday, too. Okay? Do y'all like the rule sheets? Did these help? Okay. All right. So now, who are we going to put in the center? Nitrogen. Be forewarned. There is a chance that we may have to adjust our drawing. Okay? All right, so we've got N. Now, and again, I'm asking this, how do atoms want to position themselves from each other? As far away as possible. So if I've got N and I've got 3 oxygens, what shape am I going to try to make out of this? Okay? I'm going to try to get them like this. Would you agree or disagree that those things are as far away as possible? These are as far away. Okay? Now, of my 24, how many have I used? I think we're heading into the land of some dangerous discussions here, but that's okay. We'll figure it out once we get there. All right, so I've used 6, right? So what is 24 minus 6? 18. I've got 18 left. Everybody okay with that? You see it, don't you? All right. So, again, please do not... No, actually, I'm going to do it the right way. So, once I have my 18 counted, who do I give those 18 to first? All the oxygens. I fill up my outer rings first, okay? And how many does each oxygen need? Needs 6, because they've already got 2. Stop. Shh. All right. So when we look at this, this is what we've got. This is 18. So that means I am out. I can give no more. This is where the problem turns in. When you look at each oxygen, you're like, cool, everything's great, everything's satisfied. But as soon as you look on the inside, you look at that nitrogen, an alarm should be going off. What's that alarm? It's only got 6, so it needs what? It needs 8. So let's look at step number 8. Okay? If the central atom is not yet surrounded by 4 electron pairs, except for boron, convert one or more terminal atoms. Now, who are the terminal atoms in this case? The ones on the outside, the oxygens. Lone pairs to a double bond. Now, again, only carbon, nitrogen, oxygen, phosphorus, and sulfur can do this. Is this one of the ones that can do that? Nitrogen. Now, here's my hard question for you. Which one do I take it from? It does not matter. This is what this is called. Starts with an R. Resonance. Okay. Here's what resonance is. It's multiple ways to draw the same compound with the help me out of how to word this. I want to say double bond and triple bonds. Would you guys be okay if I say the multiple bonds? Okay. The quote multiple bonds in different locations. Again, I know that this does not pertain to anything that we're specifically referring to in this chapter. However, I think it is pertinent for you guys to see it. Justin? I don't care. Just write it. Where's Jim Millen? Alright, so here's what I'm going to do. You don't have to. Don't worry about the spacing. So I'm just going to do it like this. Alright, so when I draw this is the important part. Thank you very much. Okay, all these need negatives. This is the important part. This is why I want to stop right here. Again, you don't have to draw this if you don't want to. The purple bonds are different from the red bonds in what way? Well, they're single and double, and you are right, the double bonds make it a little closer, a little stronger. Okay, if I put one karate board in front of you or 2 karate boards, which one's harder to break? 2. Okay, all right, so the next thing is, if you were to finish drawing this thing and you had to add your extra electrons around this, would the purple oxygens have the same number of lone pairs around it as the red oxygen? They would not. How would they be different? Very good. So you got these 2 pair, and then here, these are going to maintain their full 6. And again, I know this is kind of laborious, and I hope that we don't ever have to do this. And I'm just going to stop right there. Okay, but you guys get the picture. So that's what resonance means, is that, read it again, multiple ways to draw the same compound with the, and I guess that's what you're referring to earlier, with the multiple bonds in different locations. Okay, that's essentially what we're doing here, is we're rationalizing how it can be. So with the multiple bonds in different locations. Yeah, we're not even that's there's something called chirality or chirality, and it's left-hand right-hand rules, and it's how you can take them and overlap them, and they're different because they're left-hand right-hand. Don't worry about that. No, you would need to draw it. all 3 times. On May 1st, draw it all 3 times. I'm going to be honest with you. I have very rarely seen a resonance structure drawing. I've seen 1 or 2 over the years, but very rarely have I seen them. And to be honest with you, I don't think they'll ask this type of question anymore, simply based on the fact, does it really prove you know what you're doing to draw it 3 times? No, I think they would want to know, does it have resonance, or can you draw a complex structure? Can you answer more about the bond angles and shapes than drawing a picture? That's the way I view it, but again, I could be completely and totally wrong. Potentially. Yeah, if it says, if you figure out, if it says draw this structure, and you figure out that it has resonance, you have to draw it all 3 times. With different, again, if it's May 1st, you got to go full throttle. Like, you got to do the whole thing. Don't worry about timing or effort or energy or the pencil wet. Just do it all. Okay. Hopefully you got some more. All right, real quick, irregular oxidation states, I don't want to scare you. None of my tests, none of my worksheets, none of the AP exams that I have ever seen have done this. But hypothetically, I just want to show you in case something were to happen. Okay? So, beware, there can be non-integer oxidation states like an Fe3O4. Okay? There's a -8 for the 4 oxygens divided across the 3 irons to give you 8/3. Let me show you what I mean. And again, I've never seen one like this, but just in case, would you agree we'd set this thing equal to 0? Okay, why? Because it's neutral. Okay? Alright, so this is -2. Bring this down, this is -8. What do you need to make this neutral? +8. Alright, what do is you go up. So it's +8/3. I agree with you. Don't worry about it. Again, don't worry about it. Don't worry about it. Because it's supposed to be -2. When you uncrisscross your charge, I agree, but your oxidation state is still 8/3. No, the charge of it is holiness. When you reverse to find the charge of the transition metal, this is 4+ and this is 3-. Why did I show you this? Y'all are overcomplicating it. Don't. Iron's only 2 and 3. Alright, so exactly. So calm down. It's not real. Chill out. It's not. I said that. God. I did. Hey. Now, you can also write netonic equations to describe redox reactions, right? All soluble strong electrolytes as ions. That's the bust. So if you, beside this little second bullet where it says write all soluble strong electrons as ions, write bust beside that. And then it says eliminate the spectator ions. What would that be? That's your cancel, so your VBC. So we're going to balance, we're going to bust it, and we're going to cancel it. So written as is. Is y'all filled in all the way, or does it look like this? Oh, so y'all don't even have the ionic part of it. All right, well, all right, that's fine. So as you can tell, this is the way it looks. So what part of this, the complete ionic, or complete ion, what would you cancel out of this? Okay, is zinc the same or different? It's different, so it stays. Is hydrogen the same or different? It's different, so it stays. Is chlorine the same or different? It's the same, so what does it do? It goes bye-bye. So, this is a charge, and this is a diatomic. It's the ion. No, sir. Why is this weird? It is single replacement. Okay? Write the net ionic based on what's left. Thanks for writing it down. Appreciate that. Yeah. It's okay. Alright, so it should be Zn plus 2 H pluses yields Zn2 plus H2. That's what it should be. Okay. Now, Remember, this is something new. We've always used to just balance your charge, your atoms. Now what do we have to also balance? The charge. What is the charge on the reactant side? All right, let me ask you this. Again, we're splitting it down the middle. So what is the charge on zinc? It's neutral. What is 2 times 1? So this side is positive 2. All right, what about the product side? That's positive 2, and that is neutral. So do your charges match? Yes. Here's the part where people get confused. Do both sides have to be neutral? No. They just have to be what? The same. They've got to be matching. They've got to be the same. Okay? All right, so let's move on to the next one. All right, that shows you well done. Great. All right, so see if you guys can write the complete ionic, write the whole, write the complete ionic and anionic equation for the reaction. Which element? Do y'all have that? Do y'all have the whole, anything else? All right, so here's what I want you to do. Write just an anionic and see if you can determine which element is being oxidized and which element is being reduced. And think about oil rig. If you see if you can mentally bust it. Okay? If you need to write out the complete ionic, that's fine, but I want you to get to the part where you can mentally bust this thing. Can I give you a hint? Think about your solubility rules. That'll help out a lot. Well, I understand that, but if it's always soluble, do you ever need to write it down? Yep. Anytime. All right, so this is what you possibly could have written if you did the complete ionic. Okay, so you've got Al solid. Why did it stay solid? It's a solid. Leave it alone. Why did the nickel 2 nitrate bust? It's aqueous. Okay, why did the aluminum nitrate bust? It's aqueous, and why did the nickel stay nickel? Exactly, by itself, and it's a solid. Leave solids alone. Okay, so then we're going to cancel out the things that stayed the same. Did aluminum change or stay the same? Changed, leave it alone. Nickel, change or stay the same? Change, leave it alone. Nitrate, change or stay the same? Stay the same, so what do? Cancel it. Okay, so you should have had this as your reaction. Now, here's what would have happened. Let me show you my method. I'll come back to it. You know what I would have done? I would have said, nitrates don't belong. I'm going to get rid of them. So that means that I need aluminum. I know nickel is aqueous, so that's going to be Ni what? 2 plus, right? Then that would have given me, okay, aluminum is aqueous, so I know it's an ion, so that's Al3 plus plus Ni. Now, had I written it like that, it's wrong. However, here's why it looks okay. If you simply balance for the atoms themselves, how many aluminums do you have? 1 each. As it's written, there's 1 on each side. How many nickels do you have on each side? 1 each. So guess what? Checked off. I'm good. I'm ready to go. However, the new thing we must have to balance for is also now what? Charge. As it's written, what is the charge on the left-hand side? 2 positive. What's the charge on the right-hand side? That's a problem. Now, you treat this the same way you treated balancing subscripts. Y'all have a rule for that? The 2-3-6 rule, right? So if I've got a charge of 2 plus, what can I put in to make it? All right, so that's going to give me a charge of positive 6, right? Over here, what can I put in front of the aluminum? That's going to be 2 plus, so that's also positive 6, right? Does that make sense? Now, I've just unbalanced the what? The atoms. Can I fix that? Yes, okay. What do I put in front of the aluminum on the reactant side? Put a 2, and over here I put a 3. So do you see there's different ways to approach it? Yes. The reason I knew that is because it's a soluble compound always. So it's a spectator. And that's what I meant by if you know your solubility rules, it'll make them come in. The ions are. Very rarely. There are a few exceptions if you were to start out with a solid But if it says aqueous, get rid of it. You won't need it. Okay, yes, sir. Okay. You could have, yes. You absolutely could have. Yes. I absolutely agree. You're seeing the depth that I'm wanting you to get to. There are some people that haven't quite gotten to that depth yet, but you're already seeing it, which is good. Okay. Don't use the first 10. 1 is right there. Goes down to 10. 11 starts back at the top, and don't do the last ones because there's only 4 questions. Okay. That should be with it. All right. So, any questions on this? There's your answer. So let's talk about what reduced and let me actually back up so I can get my answer back up here. So now we need to talk about what reduced and what oxidized. So again, I always start with reduction, and reduction is a what? A gain, but it drops in charge. So aluminum went from 0 to 3 plus. Nickel went from 2 plus to 0. So which one dropped? Nickel. So nickel went through what process? Nickel went through reduction, and that automatically makes aluminum go through what? Oxidation. Very good. You did. If it's by itself and neutral, it's 0. Okay. Okay, go ahead. Yes. Okay. Alright, so we've already done this, so let's roll on through. Alright, see if you can do this one. There is no net ionic. How can you look at that reaction and tell there's no net ionic? They're all solids. Does that make sense? They're all solids. So what I need you to do is identify which element is going through oxidation and reduction. Let me ask you, this is really simple. How many total different elements are present in this entire reaction? 2. Who are they? Aluminum and iodine. Does that make it really simple? Aluminum's got to go through 1, and iodine's got to go through 1. Your job is to figure out which one goes through which. This is basically your oxidation rules. All right, so let's look at this. So when I want to assign my oxidation numbers to aluminum, iodine, and then Al, I3. So my first question is, when you look at aluminum, the part about oxidation numbers that throws people off is, what do you do with the coefficient? You completely ignore it. Don't act like it's not even there. Okay? You can kind of hide it like this. So the deal is that we just need to look at aluminum. Okay? Is it charged or neutral? It's neutral. So you'd set it equal to what? 0. Well, what's the only way to make it 0? 0. Okay? So that means aluminum is going to be 0. And the other rule is it's by itself. There's nothing else it's reacting with. Okay? Iodine, charged or neutral? Neutral. It's by itself. Now, the only thing that kind of makes people kind of cringe to that is because the fact it's a diatomic. But remember, it's still going to act like it's by itself. But when you get over here, it's a little different story. So let's kind of look at what's going on. So is it charged or neutral? Set it equal to 0. Okay? All right. This time, is anything by itself? No. Are there any parentheses? Do you see a metal? Who is it? And what's aluminum's charge always? Okay, +3, so bring that down, so that's +3. So what does that have to be right there? -3. All right, and what is -3 divided by 3? -1. And let me show you something interesting. What group number is iodine in? 17. What's the charge of 17? There it works. Okay, so now let's look and see what happens. Again, I always start with reduction first. I want to find out which value went down. So aluminum is 0 to +3. Iodine is 0 to -1. Which one went down? Iodine went down, so that is reduction. And aluminum went up, so that is oxidation. Now, what Dustin was just saying should make complete sense if you heard what he was talking about. Aluminum is sitting there with how many valence electrons it wants to give off? 3. It wants to do what with these things? It wants to lose them. Oxidation is a loss. Iodine is sitting there with 7 valence electrons. What does it want to do? It wants to gain 1. So iodine is sitting there like this, so it is reduction is a gain. So most of the time, your metals are going to be your oxidizing things, and most of the time your nonmetals are going to be your reducing things. Now that's not always true, okay? But for the most part it is, sir. Bingo. Exactly. Okay? Alright, so now let's look at these. My first question, do either of these two reactions need to be balanced, busted, or canceled? None of them need to be BBC'd. Why? Well, they're all solids or gases. There's no aqueous up there, okay? So here's what I need you to do. Just calculate your, or solve for your oxidation numbers and determine which element went through oxidation and which one went through reduction. Okay? This is going to take a few minutes. Just find all your oxidation numbers and then see which elements went through reduction and which one went through oxidation. You already kind of have a clue, but see if you can figure it out. Alright, so let's look at these right here. Can I give you a clue? Can I give you a hint? Always look for zeros first. It makes everything a lot easier if you find a zero first, because I'm going to be honest with you. 99.99% chance, if something is a zero oxidation number on one side, it's going to be changing on the other. Okay, I've never seen something stay neutral on both sides. Okay, look for the zeros first. All right, so in my first reaction, are there any zeros? Who? Be careful. Be specific. O2, very good. All right, so we now know that that's going to go that way. So here's what I'm going to do. I'm going to go to the other side. I'm going to start looking at those and see if I can figure it out. So I'm going to start with the lead one. Okay, so PbO. Now, here's the problem is that you guys are going to notice that PbO and SO2 both have oxygen. So you're like, well, which one do I have to do? Here's the crazy part, and this rule does not apply on this particular slide, but it will later. One element can go through both, again, this is one, ox and the same reaction. And I promise you we'll come to this later on. I'm telling you, you need to know that fact. That one element can go through both oxidation and reduction in the same reaction. Okay? It does not happen in this case, but it's possible. We'll see one later on where that does come to fruition. Okay? All right, so we know that PbO, so my first question is this neutral or charged? Neutral, set it equal to 0. Anything by itself. Any parentheses. Do you see a metal? Who is it? What's lead's charge in this compound? It's 2 positive, bring it down, so that's plus 2. What do I need to make it negative, or neutral? Negative 2, divide by nothing, so that's negative 2. So far, we've already recognized that what is oxygen doing? It's going down, so it's what? Reduction. Let's confirm that over here, okay? So we're going to set this equal to 0. All right, is anything by itself? Any parentheses? Any metals? Fluorine, oxygen, negative 2. Bring down your math. Negative 4. Okay, so this is positive 4, and so that's positive 4. So here's the thing. Does oxygen reduce in both cases to the same value? Yes. So we know that, so for our oxidation, it was going, our reduction is going to be oxygen. Okay, and we know that, now we got to figure out what our reduction is. Our oxidation. So, we know lead's 2 plus on that side. We know lead's 4 plus on that side. So let's go back over and figure out what happens over here. So what am I going to set this thing equal to? Set it equal to 0. Anything by itself. Any parentheses. Do you see a metal? Who is it? What's its charge? 2 plus. Bring that down. Plus 2. What do I need to make it neutral? Negative 2. So sulfur is negative 2. So what does lead do? Stay the same. What did sulfur do? It went up. Is that oxidation? Yes. Okay, so this is going to be sulfur. Does that make sense? We good with that? Okay, let's move to the next one. Again, the first rule of thumb is always find your what first? Find your zeros first. Are there any zeros in that one? Who? PB. So let's start with PB and let's go backwards. Okay, so PBO. I know that it's neutral. Lead is a metal. It's a 2 plus. Bring that down. That's plus 2. I mean negative 2, and I need negative 2 there. So what did lead do from reactant to product side? It lost an electron. So what is that? It went down. It went down, so that's reduction. Okay. Oxidation equals lead, not red. It equals lead. All right. Yeah. Oops. Sorry. All right. Lead went from 2 to 0. Is that up or down? Down. So that is reduction. So that is lead. Now, this kind of throws a curveball into your slinky, right? Now, because that's different from what you've expected. Again, I said most of the time it does that. You have to do the math to figure it out. Okay? So let's see what else happens. All right, so over here, oxygen is going to be equal to 0. All right, so negative 2, negative 2, positive 2, positive 2. All right, so let's go over here. 0, negative 2, negative 4, positive 4, and positive 4. So what did oxygen do in all three spots? It stays the same. What did carbon do from reactants to products? It went up, so that's oxidation. So that has to be carbon. All right, any questions on those? Good deal. Okay. All right. We're going to come back to this. I'm going to give you these rules later on. Come back to that. Come back to that. All right, that's fine. So just looking at this real quick, we'll come back to the half reactions tomorrow. Okay, so I want to get through this as quick as possible. Do you agree that sodium is a 0? Chlorine is a 0. Sodium went from 0 to 1. Is that up or down? Up. Chlorine went from 0 to negative 1. Is that up or down? Down. So chlorine went down, so it's what? Reduction, so that means sodium is a oxidation. Okay. Now, this is where it's going to get kind of weird, and I'm going to just go ahead and show you this. Notice what all of a sudden happened. What looks very odd about this. We added an electron. We split them in two and added an electron. Okay. This is what we're going to start talking about tomorrow as far as half reactions, and this will make more sense then. Okay. All right, here's what I'm actually going to stop here.